Hello everybody, welcome to the discussion for instructional question 9 for Math154. This instructional question assignment is based upon, exponential growth and approximating differential equations. The first question is based upon a regular exponential growth model for a certain population, for bacteria. We gotta answer the following questions. And the next question is based upon approximating values of a function without solving the differential equation. And that is done by the Euler's method. So we're going to start off with the first problem here. Here, what we have here is the colony of a bacteria is set to double in population every 20 minutes. Okay. And then we are starting from an initial population size of y0, which we don't know. Okay. So we're going to keep it as y0. And then the function that denotes the population at time t is y of t. So for any exponential growth function, the y of t is always going to be equals to the initial population multiplied by something raised to the power some constant times t, where this is basically the base of the exponential. You can raise it to 2, you can raise it to e, it's completely up to you. Okay, any exponential model is good enough. It will have a tweaked version of the k on top to match the rate, but it'll, overall, stay the same. So what we'll discover here, the first part they're asking us to express it with the base 2. The second time they're asking us to express it with the base e. So the only thing that will change is the rate of growth, okay? And rate of growth is just whatever that k represents on top. So for both the models, you'll see the k will be slightly different in order to, match the same rate and the same conditions that we're actually talking about. But in generality, they're both good enough models to express anything, okay? So let's start off with the first one. When you know you're going to express it with the base 2, the generic model will just be y of t equals to the y0, which we don't know, e to the power. Oh, my bad. Y of t, y0, 2 to the power of kt, because we're using 2 as the base here. So keeping that in mind, we know the initial population is y0, and then we know it doubles every 20 minutes. So assuming that my y of t is a generic exponential function with some k and some initial population, because the initial population is given to us in this problem, we're not solving that because we already know about it. The whole specified in the beginning of the problem. The only thing we're concerned about is the k value. Okay, now to solve that, we know the population doubles every 20 minutes. Okay, so after 20 minutes have passed, after t becomes 20, like right here, the population should become twice of the y0 value. So the actual equation, which I haven't written over here, is the population doubles, so it becomes twice of y0 when the time is 20. Okay, and from there you can cancel these y0s because they're on the both sides, and then you're going to end up with this equation where 2 equals to 2 times k to the power 20. Okay, and in order to make sense of this, because this is 2 to the power 1 and that's 2 to the power of k times 20, so basically k times 20 needs to be 1, and knowing that, you can solve for k, and k happens to be 1 over 20. So when you know the k value, plug it back into this function, and your model for a function with t for base 2 is going to be the initial population times 2 to the power 1/20th times t. And that's just a model for the base 2. Now if we talk about the model with the base e, we have a certain property that we already know about. Okay, for exponential models that you have with a base e to the power kt, that k right here obeys a relationship that is always going to be equals to ln of 2 divided by the doubling time. So we can use that rule here because we know the doubling time is 20 minutes. So to find the k for the exponential model, we can use the rule that we remember for e models, and then we can find the k to be ln 2 divided by 20. Of course, you can go ahead and solve it into a decimal number because this is going to be irrational, so I don't tend to solve these things usually. So now when we have the k for our equation, in our model with the exponential e base, we can replace the k value with that to get to our final result. So when you plug in that k here for ln 2 over t double, your final expression is going to be like y0 times e to the power of ln 2 divided by 20 times t. And that's this, right? That's pretty much sums up, the very first and the second part of the problem. Now, before we begin the C part, they're asking us what differential equation does y satisfy. I can kind of give you a brief overview here. So when you're trying to find that thing, for a differential equation does y satisfy. You can use any model you want. Okay, we're going to use the exponential model, but you're feel free to use any model because both of these are valid expressions of this, right? So now let's try to see for the exponential model what a differential equation is. So given this y equals to the initial value e to the power kt, you find its derivative. That's just going to be y naught is going to stay as a constant in the beginning. And derivative of exponential to the power kt is just going to be exponential to the power kt times the derivative of kt, which is k. Okay, so we're going to end up with this expression where the y prime is just y naught e to the power kt times k. And now because if you see closely, this expression right here is nothing but the y value, right? So this differential equation could be simplified into y prime is y times k. So that's the property that every exponential function obeys. When you have an exponential function, the derivative of that will depend upon itself, and that's how you can find a differential equation. So that's why any exponential growth model which uses e as a base will satisfy y prime equals to ky, or you can write y prime as dy by dt equals to ky. And that was an easy catch. Okay, you can take a derivative to prove your analysis here, but you can definitely use it as a base set as well. That's part C. Now part D is what they're asking us: at what time does the initial population grow by a factor of 3? So we're looking for the t value where the population is 3 times the y naught, the initial value. Okay, so now to find that, we can use both the models. Both the models are working fine. This one is okay, and even this one is good too. But I'm just going to use both of them to demonstrate, it's not going to make any difference. So you'll feel free to choose any one of them that you want to use. For the first time, when we use the 2-base model, we need to find the time when the y equals to 3 y naught. So we can use any model, so let's use the base 2 model for the beginning. When we see that, we replace the y with 3 y naught and a y naught times 2 e to the power 120t. We're looking for the t value, okay? We're looking for the time where this happens. So we'll cancel these up. We're going to be left with this. Now, whenever you have an exponent that's you're solving for and it's in the actual power of something, you want to bring it down. And to do that, we usually take ln, okay? Taking natural logarithm of both sides will give you ln 3 here. And a property of ln tells you if you have a ln of something, a to the power of b, that could be written as b times ln of a. So basically, you can bring the exponent down here like that. So when you take ln of 2 to the power of that, what you can do is you can bring the exponent down here and write it as 1 over 20 times t times ln of 2. So from there, we have that expression. And if you isolate for t from there, is when you divide the whole equation by, 20 divided by ln 2, you're going to get this expression here. So it's just rearranging from there and isolating for t will get you this answer. And that's pretty much it. That's the part. But if you choose the E model, similar analysis. Now you're going to, instead of using this base 2 model here, you're going to use the E model. It's going to be a little bit tedious to analyze, but at the same time, you're going to get the same answer. So feel free to walk through this if you need to. But I think any one of the models is sufficient enough for this, assignment answer. Hopefully that clarifies the first question about exponential models. In this case, if you have any questions, reach out to me. Now, after this, we're going to talk about differential equations and estimation. So we're using, just to cover up this first, we're using Euler's method to find an approximate numerical solution to a differential equation. Okay, so usually what you've done in probably of the courses, you can actually solve this differential equation, right? You can actually, learn methods to solve this. But what if we don't know? What if we can't solve it usually? But if we can't solve it, what we want to do is we're interested in finding, the value of the function at 1. We don't have the function on hand, right? We only have a differential equation and we only know how it starts to begin with. So we want to see, depending upon this growth rate and this starting value, how does this grow up to y of 1 instead of actually solving the equation? And Euler's method will help you do that. So Euler's method tells you, it's an iterative method. What tells you is the next y value, y of 7k plus 1, is equals to the current y value plus the derivative at the current y value times the step you're taking. So it's just like a linear approximation here. Okay, so let's say you are on a graph here, and this is your starting point. To get to the next point here, you're drawing a line. Okay, and that line is going to have an equation y of k. The slope is going to be the derivative at that y of k times the difference in the step that you're taking, which is delta t. Okay, so that's delta t here. And now this method could be a little bit tedious to analyze because it has a lot of iterative steps. So I'm going to try my best to explain this, but pardon me if I'm not able to. Okay, I will try to re-explain if you have any questions in personal if something doesn't make sense. So what we're doing is we're starting with this initial value. We know this. I'm using computing yk from y of k plus 1 from yk using a step size of delta t. Now the formula for this is a standard that you should remember. Okay, that's like a memory thing. So that's only the first part A. First part A is only asking you for the formula. And what you can do is, because the next k is just the previous k plus the derivative at that value times the delta t. So we're keeping the delta t because they want you to have it in terms of delta t. But you want to make sure the right side equation is only in y of k. So now because dy dt is just nothing but cube root of y, so dy dt at that yk is nothing but the cube root of yk, right? So whatever y you're looking at, you plug it in and into the dy dt, and that's what you're going to get. So pretty much have this expression here. Now if you take this and you plug it in there, your final expression is going to be yk plus the cube root of yk, which represents the derivative, okay, times delta t. And now that we have this equation, what we can do is we can plug in the initial condition to find the next corresponding steps. Okay, so what they want you to do in the part B is find the values of y1, y2, y3, y4. What these subscripts are telling you is that when you start at y0, the next value you're going to estimate is going to be called y1, and then the next one is going to be called y2, and that's going to be, dependent upon the steps that you're taking. So first time when you have y0, you take a step of, delta t equals to 1 for this case, and you get to y1. So if your y of 0 was this guy, right? If your y of 0 starts at 0, then when you take a step of delta t equals to 1, you're going to actually end up with y of 1 being y of 1, because you jump from y0 to this point. So you're going to have a delta t step of 1. However, if you do that for delta t step of 0.5, the steps are going to be different. So I'm going to talk more about that in the very end. Here they have this table they got to fill in. So what I did is I did the first couple numbers just to, give you a better idea. But this could be done without showing the work, and you could use, numerical calculators to do that. And I'm going to show you how to use that too. So here we have the initial value of y0. The next 4 steps from there, okay, because we're going to calculate 4 things. So each one of this, for this row, is going to have a delta t step of 1. So we're going to go for delta t step of 1 again, and then hop again for that row. However, for this one, when you start at y0, you're going to start at 0, but the delta t step is going to be 0.5. So y1 is going to estimate the function's value at 0.5. And then you're going to have, another 0.5, so total 1. And then you're going to have 1.5 here. And then you're going to have 2. So basically the number of steps you have is 4 for all the fixed cases. But the actual length of the step is smaller. Okay, so if you start at 0 and you got to move, start at 0, you got to move 4 steps. Well, delta t equals to 1. You're going to eventually end up at 4. So basically this y4 is the value of y at 4. But if you start at 0 and you're going to start with 4 steps again, but your delta t is, instead of 1 being 0.5, you're going to stop at 2 because you're going to increment it that way, right? Similarly for the last case when you have 0.25, so if you're starting at 0 and you're going in 4 steps of 0.25 each, you're going to end up at 1. Okay, that's why these boxes are labeled in the green, because the later part of the question will ask you to do that. So let's do that together. Excuse me. For the first part, when we have an equation in this case, right? In part A, to fill the table, for example, when you're looking for delta t equals to 1, so delta t equals to 1 in that row, because the initial value is 10, so y0 is 10, and then y1, depending upon this formula, y1 is just going to be y0 plus y0 cube root times delta t, right? So here I just plugged it in. So you have a 10 and then times a cube root of 10 times 1, because that's the initial y value that you began with. And this will give you some number, right? That will be some number that you have. I'm just going to keep it like this for now. I'm not going to solve it. So for me, y1 is nothing but 10 plus cube root of 10. Okay. Now to find y2, you're going to take this y value, plug it in. Because y2 is y1 plus y1 cube root times delta t. So y1 itself is just all what you got here. Plus the cube root of that is going to be this uglier expression and times delta t. So you can keep on filling it. Because it's going to get very ugly, I would want to use a calculator for this because there's so many values. I think it's justified to not show your work to calculate each of these numbers because it's so tedious, and you should have a leverage to do it on yourself and fill in the table. So how you do that is you go to internet, and then any regular browser, you type in, Euler's method calculator. This should be the very first link that you open up here. Okay. So this Euler's method calculator will do the iterative step for you. So just gonna get rid of the time. So what we have to do is we have to input it correctly. So here the function that we're trying to work on with is just a function of y, and that's just y cube root. So we're gonna make sure it's a small y, not a capital Y. Y, and then you gotta cube root it. So that's this. Now, because step size h here, they call it h, we call it delta t. So that's going to be different for all of the cases. Let's start off with 1, okay, because the step size we're looking at is 1. Delta t equals to 1, the first row of the table. And then the initial condition that we know, that y of 0 that gets given to us is basically 10. So you're going to put that as 10. And then what we're looking for is the final value. Because the table doesn't specify what we're looking for exactly, what we're technically doing here when we're trying to find y4, we're just looking for y of 4. Okay, because delta t steps of 1 will give you, this is 0, this is 1, this is 2, this is 3, and this is 4, because this step is going to be 1 in each of these cases, right? So technically we're solving for y of 4 to get to these 4 steps in the first one. So when we do that, let's see. Let's plug it in. And then we're going to hit calculate. Down here, you're going to get all the results. Okay. So it's going to do all the interpretation of what you submitted in there. The first time when you try to do that, if you see the step 1, the very first one, is when they ask you to compute y of t1, which is y of 1, or y subscript 1, which is what we're looking at. And that happens to be 12.1544346 and all that numbers. So you're going to take that as your first value, and we're going to pick that up and then move it into the table. We're going to add it up there. Then step 2 is going to use that previous value to calculate the next value, which is right here. We're going to take that and plug it in the second one. So that's why you see all these numbers here. The 12.154 is coming from there, and then so is 14.4542. So 14.452 is from here, and then you have a different here for 16.889, and that's this guy here that goes into y3. And then the fourth step finally is basically the y4 value that you have here, and that happens to be given on the bottom. It's 19.44455, like these. So some of these numbers might be a little bit off because sometimes rounding up is different, but of course you can double check with what you do on your calculator. My numbers might be a little bit off when I was copying it down, but yeah, you can definitely double check that. So that was the first one when you do delta t, and that's how you fill up the first row. So those numbers are here. Now for the next delta t, all you got to do is go back to the same calculator and change that step size to 0.5. Okay, so now a common sense thing is when you do that 0.5, when you're trying to compute y of 4, so starting from 0 and to reach up to 4 with a step size of 0.5, it's going to take you a total of 8 steps. Okay, and we don't want that. We want to do just the 4 steps because y4 is what they're asking us to do. So definitely we got to change this number, and instead of finding y of some number that you're looking at, that should be y of 2. Because if you're looking for y of 2, then only going to have 4 steps of 0.5 each to get to the value. So we're going to know with this and then hit calculate. I'm going to redo the math for you. And here again, the step 1 is going to give you 11 point something. And that is just approximating this value right here. And this is going to be y of 0.5. because now the one step is going to have a distance of 0.5. The next step, however, is going to be y of 1, and then y of 1.5, and then y of 2. So we're going to do that here. If you look at the other steps, it's very similar. You copy this down. The next step is going to be 12.191. That's why you have it here, 12.191. Then you can go back, you go back here. That's step 3, and step 3 is 13.342. So we have that number. And then 14.52. So 13.342, 14.52. That's this. So that's how you compute this value for this table. And then for 0.25, as you guess, it's going to be very common. But now because we're stepping in 0.25 and starting at 0, we're going to go up to 0.25, and then 0.5, and then 0.75, and then 1. So basically we need a y of 1 value here. So we're going to go back to the calculator and edit that. We're going to change our step size to 0.25. And then the value that we're estimating is y1 for 4 steps. So you click it in, and all the numbers are going to be in front of you. Step 1 is 10.53, step 2 is 11.86, and then step 3 is 11.64, and step 4 is 12.218. So you take all these values, round them up, and you fill up this thing right here. And that's how you fill up the table. And I know this is probably the a faster way of doing it, but that's pretty much what you do with numerical methods. Usually computing all of this approximate methods, you use calculators all the time. So I would say it's okay to do that, but you can double check once with your prof. Do you actually show the work or not? If you show the work, then you have to write it out like this, like I did. But luckily, I hope you don't have to show the work, so you can use the formula from the Euler's method. Now, the C part is asking you, state all the estimates of y of 1 computed in the above table. So what's happening here in the first table, in the first estimate with delta t equals to 1 step, right? We're estimating y of 1 here. This is the row where we estimated y of 1. But when you're using a step of 0.5, you're starting at 0, you're going to go to 0.5, and then you're going to end up at 1. So y of 1 in a 0.5 step is going to be estimated on the second step. And that's what's y2, right? But now when you're doing it for 0.25, okay, because it's going to start at 0, then you 0.25, then 0.5 here, and then 0.75, and that's going to be 1. So y of 1 is pretty much the estimate on the very fourth step for 0.25. So that's how I literally label it up here. For index for this thing, right, for different delta t, we have different index. So here, when you're looking at delta t, y of 0, y of 1, y of 2, y of 3, y of 4 are representing 0, 1, 2, 3, and 4 respectively, because the step distance of delta t is 1. Okay, so to estimate y of 1, we need y1, and y of 1 is roughly going to be equals to y1 of the first table. Okay, and then we got the first row y1 to be 154. My bad. Let me correct that in. Okay, because it's 154. So that's like my brain not working properly to copy it down. That was that. Now for delta t equals 0.5, all of those numbers, y1, y2, y3, y4, are now representing the steps of 0.5. So y1 is going to be representing 0.5, and y2 is going to be representing 1. So y of 1 value estimate from the second row is going to be the y2 value in that row. And that happens to be 12.191, and you copy it down here like that. And now for the last one, when you have delta t equals 0.25, all of these steps will have a difference of 0.25. And the value of y of 1 is going to be estimated by y4 of the last row. So y4 of the last row is 12.210. And that's how these are estimated. Now you see they're very close to each other, okay? Because all of these values are going to be somewhere like 12.14, 12.2, somewhere there. And the reason why they're so close is because we're trying to estimate the same value, but in different number of steps, okay? It's just like more resolution you have, okay? If you want to jump up to, let's say, one value to the other, the more tiny steps you take, the better accuracy you're going to get. Okay, so if somebody was to ask you what's the more accurate value amongst all of these three for a better representation of y of 1, that's going to be the one with the highest resolution, because you're taking a lot more steps to get to 1. In this case, you reach to 1 in 1 step. In this case, you reach to 1 in 2 steps. In this case, you reach to 1 in 4 steps, right? So the number of steps are increasing and the interval of steps are decreasing. So you're going to estimate better values, and slowly moving towards the better value is going to give you more accurate result. And that's why this is a more accurate one. Of course, that's not required as a part of the question, but that's just a good thing to know. So with that, we conclude the discussion for this one. If you have any questions, you know how to reach out to me, and all of these, the PDF of the solution is going to be in the description of the video. Thanks for watching, and I'll see you next time.